Good evening, everyone. We're going to go ahead and get started. Second video. As you can see from the top, this is taken from section 6.3 in your textbook, talking about Hess's Law. Now, Hess's Law comes into play when we deal with, let's tie it in the last unit. Remember last unit we talked about mechanisms for a short time, and we talked about the fact that there are many reactions that can be broken into multiple steps. Okay, now with that in mind, if we have a reaction, it could take place in one step or it could take place in several steps, but the amount of energy change or the change in enthalpy is going to be the same. Okay, now let's take a look at this. We're given the reaction at the top, nitrogen gas plus oxygen producing 2 nitrogen dioxide. Now, this reaction is going to happen, and it's going to produce 68 kilojoules of energy. The same reaction could be, or same process could be described through the formation of forming 2 nitrogen monoxide and then adding in the other oxygen to produce 2 nitrogen dioxide. In the process, you notice we're going to have that change. We have 180 kilojoules produced, or needed, for the reaction to happen between nitrogen and oxygen. And then we have 112 kilojoules released in the process when we actually form the 2 nitrogen dioxide. When we add these two enthalpy changes together, we get 68 kilojoules, which is the same thing that we started off with. Now, in canceling these out, we end up with, our final balanced equation, just like we talked about before. The overall principle is this. The energy that's going to be released in each of these processes is going to happen regardless. I need these different parts in order to form my compound. So, in that process, whether it happens as a single step or whether it happens as 2 steps, my final energy result is exactly the same. Okay? Now, we have to do a good amount of practice in these because I want you guys to be very comfortable with Hess's Law as far as understanding and putting it into practice, because you're going to need it as time goes. Now, if we're looking at an enthalpy change, say we're looking at the second step but going in the opposite direction. If we change the direction, we change the sign. Okay? Now, so if it was negative, and usually to form it, it's giving off energy. When we are getting rid of it or going to break it down, we'd have to put in energy. Okay? Now, the magnitude of H is directly proportional to the quantities of reactants and products in the reaction. If the coefficients in the balanced reaction are multiplied by an integer or coefficient, the value of delta H is multiplied by that same integer. In other words, if I'm looking at the reaction, everything is usually set on 1 mole. So if I'm going to have 3 moles, then that means I'd have to take the amount of energy produced and multiply it also by 3 moles, or by 3. This would allow it to be proportional. Okay? So taking a look here, this is an example that we actually sort of want to walk through. So we're given that ammonia gas breaks down into 1/2 mole of nitrogen and 3/2 of mole of H2. In this process, delta H for this is going to be 46 kilojoules. Similar thing if we look at hydrogen forming water. We have 2 hydrogen gas, with 1 oxygen gas going to produce 2 water, and we get delta H is a negative 484 kilojoules. Now, I want you to go ahead and step in knowing this information and see what would be delta H for this reaction. Well, how can we attack it? Well, work backward from the reaction. So we want to be able to look at the overall steps, I guess, and use those to gather our information. Then if we have to reverse any reactions, then we'll reverse the sign so that we can end up with the correct values. Then multiply the reactions to give the correct number of reactants and products. So we're going to go ahead and reverse the two reactions. Why? Well, if this is what we're given, we're looking at these being our reactants, these being our products. So if I flip it, that's going to flip the sign of my delta H values. Now, with this part done, now I need to do some multiplication because I had 1/2 nitrogen, but I need 2. So I'm going to end up having to multiply it out. Same thing here for my hydrogen in forming water. I need 6. I have this value, which is based on 2 moles of water. I need 6. So multiply this one by 4 and multiply this one by 3. Because 4 times 1/2 will give me 2. So if I continue on this way, this now fits my original idea. Now all I have to do is calculate my energy change. My H2 is gone, and I get 1260 by adding these two up. Were you able to keep up? I hope that you were. Now, really quickly, we're going to look at standard enthalpies of formation, which is basically looking at how much energy it takes to form in some of these compounds. Now, for many of them, we're going to look at them in what we call their standard states. For a compound, we're going to look at a gas is at 1 atmosphere. For a solution, 1 molar, and a substance, pure substance, it's either a liquid or a solid. For an element, we look at it exists in 1 atmosphere at 25 degrees Celsius. That's standard room temperature. Now, overall, we're looking at what are the things that happen to form that compound, okay? So if all of these are my reactants, this looks like methane plus oxygen gas. Notice that for oxygen, we have 0 kilojoules for it to form. Why? This is something that would go back to honors chemistry, which you learned last year. What do we know about the diatomics? Same thing here. When we break this down, carbon into the 4 hydrogen. Once we form these 4 hydrogen, what real change do we have? Well, not much, because they form this way on their own. But as this change occurs, and now we have our hydrogen forming with water, and our carbon dioxide happening here, we're going to get some other adjustments, I guess we'd say. But for oxygen, notice that it is 0 kilojoules of energy. That is actually important. Now, when solving problems for enthalpy, we're going to make sure again, if the reaction is reversed, then we need to flip the signs. Also, make sure if there are coefficients out front in the equation, we multiply the amount of energy, the delta H value, by that coefficient. If we don't, we're going to have some serious problems. That's why I'm making sure to repeat it a second time. Overall, we're going to look at the change in delta H, and we talked about this before, the change in delta H for the products minus the reactants, adding it all up, and we did this back in Big Idea 2. Now, I'll leave you with this, and I'll take a moment, say pause here, and I want you to actually calculate the delta H for this reaction based on the standard enthalpies of formation, which you see here. Take a moment, write everything down in your notebook, and we're going to go through it in class. That's where we're ended here. Have a good day, and see you later.